Yeah. Please tell me that I can't, that I won't, that I fail, that I'll never make it out, yeah. Please tell me all the bad, never good, fill my head full of every single doubt, yeah. Please say any negative thoughts, I pop off when I hear people say I cannot. I get off to the thought of proving everyone wrong, I won't stop.
Hello my friend, today is Fractal. I'm gonna code this from inception to conclusion so you can appreciate how I tackle a problem like that, right? In which we have to create a little application, namely many files that have to cooperate to create something, not the usual hello world application, which you have to solve only one function. Okay, by now you should have a good understanding of the minilibX. So if you don't know, just watch the previous video I made or search some sources online, and you need to know what is the fractal idea, what is a complex number and all that stuff. So I made a little explain like I'm 5 introduction. You can watch that, or in the description I leave some links into some very good videos that I think are really worth watching. All right, that's it. We start. It's going to be kind of longish. I think I will cut all the silences. I have an algorithm that is cutting all the silences. So I will leave you only the the cool parts. All right, let's start. So hi, this is me from the future, destroyed. My brain is not working anymore. I coded this little application in C. So you can check the video. It's pretty long, I guess. I don't know how it's going to be. And basically, this is the final application that I made. It's not performance-wise amazing. I mean, we need to put some steroids to it to do the zoom more linear and so forth. You will see. But I think that you have all the principles that you need to create your mandelbrot sets and explain to me how it's really done. Okay, I hope you enjoy. Thank you for watching. So we want to draw this marvelous object here. This, my friend, is a fractal. What is a fractal? Asking ChatGPT we get, imagine you have a drawing of a tree. This tree has big branches, and at the end of those big branches, there are smaller branches that look just like the big branches. The smaller branches, there are even tinier branches that also look like the big branches. So no matter which branch you look at, big or small, they all look similar. A fractal is like a tree. The same pattern keeps showing up no matter how close or far you look away. It really seems that nature loves fractals. As you can see, we have broccoli. Broccoli are self-repeating structures. Then you have pine cones, snowflakes, as you can see, have this self-similarity, right? So you have self-repeating structures, of course, trees, and so on, right? You understood the point. You can see that there are many kinds of fractals. I would argue that this is a marvelous piece of art. Look at those beautiful images. And the most famous, of course, is the mandelbrot set, which is this fractal here. You can endlessly zoom in and you will keep finding these self-similar structures. So in this video, we are gonna try to render this object using C code. So we have to understand some math concepts. Especially we have to understand complex math. So to understand complex numbers, we're gonna start from the first principles, from the beginning if you want. So we have numbers, right? You perfectly know the line number in which you have plotted 0, for example, 1, -1, pi, which is 3.14. Here you have 3, -3, -4, and so on, right? All the numbers that we know very well, that we use on a daily basis, and that's it. We understand them. Super easy. Now, what are these numbers? Well, if you think about that, these are just abstractions. These are just abstractions to describe the world, if you want. To describe the world. To keep count of stuff. You know, numbers are just a human construction. They're not out there in nature. This is just how we abstract stuff from the real world. So to say I have 3 things, we say I have this symbol things, okay? I don't have to draw, for example, like back in the days, the cavemans, all the objects, for example, 3 apple. We have this special symbol that is gonna abstract away the real thing and describe the quantity. And as you can see, I have 3 lines, if you see. 3, this is the number, 3 lines. Indeed, the symbol recalls the number of objects, 1, 2, and 3. For example, the number 2 is the symbol here that is made like that. I have 2 lines which are linked. So I have 1, 2 objects. The number 1, of course, is the symbol here because it's only 1 line, and so forth. So take home message, numbers are just symbols, human created to represent stuff which is in real world. So now let's search for these values. Square root of 1. What is the square root of 1? Well, is equal to 1 because 1 per 1 is equal to 1. Of course, when I say square root, I'm implying what is the number that multiplied by itself is going to give me this value. So square root of 1 is here. Square root of 1. is plotted inside in this place. Now the catch, I have this value, square root of -1. What is the result of this? Well, it's kind of a conundrum, right? Because when I multiply a number by itself, I'm gonna get forcefully a positive value. For example, +5 per +5 is equal to 25. This, of course, is 5 squared. What if I do -5 squared? Well, I get -5 per -5. I still get 25 positive values. So I cannot have the square roots of a negative number. Or can I? Well, it turns out that having the solution to this problem was particularly useful for mathematicians, you see. So mathematicians came out with a cool idea. That is, we need this value. So what shall they do? Well, they invented this concept, which is of imaginary values. What does it mean? Let's say the square root of -1 is equal to I, okay? So now we have that we can have the square roots of negative values. And everyone, of course, was super happy about that. All the mathematicians were super happy. Now we can solve our stuff. See? So this I for imaginary is a very strange nomenclature because it implies that this kind of fake doesn't exist. But we can argue that all the numbers don't really exist. They are an abstraction that our mind has created to describe stuff that exists in real world. But if you stroll around, you won't find a 3 or a 4 or a 5, you see? These are just ideas in our mind. Think about negative numbers. Negative numbers. What is a negative number? If you have to explain to someone, why -3? What is -3 things in real world? Can you have negative things? Right? What is the sense? Can you have -3 apples? No, you cannot. Indeed, this is a very cool abstraction to keep track of credits and debits. So negative values are fairly useful in real world. Why I say this to you? Well, because I want to emphasize that everything is just a creation made by humans to solve problems, as well as this one. This is a creation made by humans to solve problems. Indeed, this abstraction turns out to be fairly useful when you want to solve different mathematical problems. In our case, in our programming case, when you want to plot a mandelbrot set. Now, where can we find this I inside our plot? We cannot find this number here. We have here only natural, real, rational numbers. So where we have to check? Well, we have to change perspective a little bit. We have to check here in this axis. You see, now we have that we have a real axis and an imaginary axis. So here we have, for example, 2i, 3i, 4i, minus 2i, minus 3i, and so forth. You get the point, you see. So we have basically a complex plane. So let's take a point in this complex plane. Let's take, for example, it's 4, this is 5. Let's take 5, 2, this point here. So this point is 5 real and 2 imaginary. This, my friend, is a complex value. Why complex? Not because it's difficult, but because it's made of different parts. We have indeed a real component and an imaginary component. Indeed, the opposite of complex is not easy. It is independent, you see? So complex means made up of different parts. So a complex value very easily is made up of 2 different components. So as you can see, this complex plane is exactly the same as a normal 2D Cartesian plane, right? In which we have the x and the y coordinates. And here we plot our points. For example, here we have the analog point on a different scale, as you see, which is 5, 2. In this case, we have 5x, 2y. You see? That's exactly the same idea. And indeed, that's what we're going to do in this video. We're going to use complex value as they are values in a 2D Cartesian plane. Of course, we have to keep in mind that these are not x and y normal coordinates, but they are complex values. So the math is specific. Indeed, the math is different for complex values. And the only piece of math that we're going to need is exactly this. So when I square a complex value, I get -1. That's basically all we need for our purposes to draw the mandelbrot set. All right, this is a very silly introduction to the complex numbers. Now, if we read from Wikipedia, the set is defined in the complex plane as the complex numbers c for which the function z is equal to z squared plus c does not diverge to infinity when iterator starting at z equal. Oh my god, this is so confusing. But you will see that it's not that terrible. I will try to explain very easily what is going on. So here, as you can see, we have the plane. This is a complex plane, but you can perceive it like a normal 2D Cartesian plane with the x-axis and the y-axis. Of course, this is the real and the imaginary axis. So we have the mandelbrot set here, which is the black stuff. All the points in this specific plane satisfy a specific condition, which is when iterated in this function that you will see, z squared plus c, the point does not diverge into infinity. You will get this point with the practice itself, don't worry. But now bear with me. You see, when I move these dots inside the mandelbrot set, I have all the subsequent points which are bounded inside this area. When I go out, you have the points that escape. Somehow they reach escape velocity and they go very far from this black mandelbrot, you see? So we have that all these points with the specific real and imaginary x and y components satisfy the function and are part of the mandelbrot set. So we draw a black pixel here when we have satisfied the function. Let's see this in practice. So the function that has to be satisfied is this one. F of z is equal to z squared plus c. These z and c are complex numbers. We use z for pointing out that this is complex math. Let's again draw our 2D plane. Here we are. We have the real and the imaginary. 5 and 2i. Let's take again the point of before. 5 and 2i. Here we are. So I have this complex point, which is 5, 2i. Now the question, is this point in the mandelbrot set? Namely, is this point here, so 5 real, 2 imaginary in the mandelbrot set? As you can see from the image, no, of course. Immediately the point escaped to infinity, but let's understand why. So c is the point that we are looking, so is this one. While z will always start from 0, 0, okay, for our iterations. So we say z0, so the first iteration is equal to z squared. In our case, it's going to be 0, 0, so the result is going to be 0 plus c, which is the point, so 5, 2i. So z0 is going to be equal to 5, 2i. Easy. Let's go to z1 and let's check if this value stay bounded or escape to infinity. Now I have to do z squared, right? Which is this value, so 5 plus 2i per 5 plus 2i. This is z squared, you see, squared, plus c, which of course is 5, 2i. Now, here we are in complex math land. And you know that our mathematicians, friends, told us, remember, I squared is equal to -1. So how do we solve it? How do we square a complex number? Let's see here. So of course we do the usual algebraical transformation, right? We multiply all the members like that. So what do we get? 5 per 5, 25, plus 10i, plus again 10i, plus what? And here is the strange part. 2 per 2 is equal 4, plus I per I is equal to I squared, which is this one, it's -1, see? -1. So I get 4 per -1. So I get 25 plus 20i minus 4. So I get 21 plus 20i. What is this, my friend? This is a complex number again. This is a complex number which has 21, the real, and 20, the imaginary component. You see? So we managed to square the value. So z1 is going to be equal to 21, 20 plus 5, 2. For the sum, it's fairly easy. It's like vector addition. So you do 26 and 22i. So the next iteration of z1 is going to be this value. So we jump from here to here. As you can see, the points are already going far apart. I have 26, 22i. And indeed, look at the point here. Look at the points that we have. 26 in the real part and 22 in the imaginary part, you see? Now, in the following iteration, I expect to see the value going very, very far from the mandelbrot set. You see how far it is going? Like here, a gigantic value for the real and the imaginary, like 200 and 1100. On the contrary, let's try another point. Let's try another point that is part of the mandelbrot set. So let's take, for example, the point -1. As you can see from the animation, if I go to -1, I have this behavior of the point. Let's understand why. So in our complex plane, let's take -1. This is -1 real and 0 imaginary, right? Let's feed into our function. Z squared plus c. Initially, z squared is always 0, 0. So the 0 iteration is going to be z squared 0 plus c. So -1. What do I get? z0 is equal to -1 and 0. z1 is equal to -1, 0 squared plus -1, 0. Let's solve it. -1 plus 0 per -1 plus 0. I get +1 plus 0 plus 0 plus 1 is the result. So I get +1 minus 1, 0. Okay, theta 2 is equal to 0, 0 square plus minus 1, 0. As you can see here, we are back to the beginning. We are back to the first one. And we get, of course, minus 1, 0. So you see, like, we are getting this toggle effect. We're getting this toggle effect. We go here, we go back and forth here, back and forth, back and forth. Indeed, this value stay bounded in this specific area. So this, my friend, this is a mandelbrot point. Why? Well, because this point stay bounded given the function, you see? I have this toggle effect back and forth. This is a mandelbrot point. That's all there is, my friend. So now, my friend, let's implement those ideas in code. So I'm going to do a program, I don't know, complex plane.c. Boilerplate include studio.h. It's main. So immediately I create my complex value. I do a struct, so typedef struct complex. Of course, we are going to use doubles. Double, real, this is the x component, right? In a Cartesian plane, but this is a real value. And then, of course, we have the y component. So we do double I for imaginary. Okay, this is type complex. So now we are going to do a simple program that checks if a specific number is in the plane. So I'm going to say type complex point. So we're going to start from this complex value 5 to I and apply our function here. So we said that initially z is going to be equal to 0, 0, and c is going to be a point specific in our plane, essentially this one. Let's do that. So let's change it to do exactly like the formula, type complex z and type complex c, which is, of course, our point. Okay, c is the point. Z, we said that is equal to 0, 0 in the first iteration. On the contrary, the point c real is equal to 5, okay, for the real component, and for the imaginary component, the one in the y-axis, it's going to be equal to 2. Okay, we're going to do the iteration, I don't know, 42 times for equal 0, I minor than 42 plus plus I. What do we do now? Let's derive a general formula. Z equal z squared plus c. So let's understand how to square a complex number. Let's derive this formula. So we have our 2D plane with our point. Here it comes. We say that this is our x and y, real, of course, and imaginary. So let's pretend I have this point, which is 2, 1, let's say 2 and 1 I, or simply I, but anyway. So the general formula that I want to derive is x plus yi squared is equal to x plus yi per x plus yi, right? Logical. We are gonna do all the necessary multiplications and we see the results. So we get x squared plus xy imaginary plus xy imaginary plus y squared and I squared. And here now we understand that's the tricky part that comes from complex math. I squared is equal to minus 1. That's the rule that you have to remember. So what do we get? X squared plus 2xyi minus y squared. So we have this x squared minus y squared plus 2xy imaginary. And this, my friend, is the new complex number. Namely, I have this and I have this. This is the imaginary component and this is the real component. So this is the general formula to get the square of a number. In the real component, you have to square x and y and subtract. For the imaginary component, you have to multiply 2 per x and y. That's it. That's the formula to square a number. So here I'm going to create a variable that I call temporary real. You will see immediately why. And I do temporary real. I want to stock here the squared z real component. So I need this formula here, right? Z squared minus y squared. And I will get the real component square. So very simply, what do? I do z real per z real minus zi per zi. That's it. Of course, here when I say x and y, I imply real and imaginary. Then for the imaginary part, I have to do 2xy. So real, imaginary. So it's going to be 2 per z real per zi. That's it. Now, of course, we update the real part. So z real is equal to temporary real. Here, of course, I use the temporary variable because here I needed to use the z real part. Okay, we are ready. Now we just need to add c. So adding the c value. So we do z real plus equal c real and the same zi plus equal ci. Okay, that's it. Now we are gonna print the values. So %f, iteration number, %d, real and imaginary. Okay, so now we plot in I, z real, zi. Okay, that's the code. Let's see what we get. So I'm gonna run complex plane. So as you can see, we have iteration 0, and I have, of course, 5, 2, which are the initial value. Then we go to 26, 22, which is exactly like we saw before, right? 26 on the real and 22 on the y. Then we go 197, 1146. Indeed, I think this is correct. 197, here you have 200, and indeed it's 197, yeah. At the level here, 1146. That's the new point given the iteration. So that's what we mean when the point escapes the mandelbrot set. You see, these are all the operation, and immediately the point escapes. He is not bounded on a certain value. Now let's search for some values which on the contrary are inside the mandelbrot set. For example, let's do 0.25, 0.4. So let's do 0.25, 0.4. Okay, let's launch again. And as you can see, the value stay bounded, doesn't escape. And this is a sign that this point is exactly part of the mandelbrot set. So the first iteration I get 0.15, 0.6. As you can see here, 0.15, here it comes here, and 0.6. Then we go here to the minus. It seems like everything is working, right? Then we go down, and then again we go back on the plus. I have 0.16, 0.35. So 0.16, 35, 0.35. It seems like it works correctly, right? But overall, you get the idea, you get the point. Now, I think you have all the math theory that you need to do the project. Perfect. We are going to use the minilibX for Linux. There is also, of course, the minilibX for macOS, but I think the Linux one is better, more complete. You will see why. So, given that I am working with macOS, I need to start my virtual machine. So I open VirtualBox and I start my Ubuntu system. Start. If you now are thinking what the hell is saying, you just watch this video. Create a local Linux server in VirtualBox by Livia Lima. By the way, I highly suggest to subscribe to the channel if you're interested about operating systems, especially Linux. So my virtual machine is loading. The problem is that when you work on a virtual system, everything feels really clunky, especially if you have a slow computer like mine. I have a 2017 macOS, still with Intel chip, so it's basically impossible to work there. I will SSH from my macOS system into my local virtual machine, so I can work on my macOS. I will launch the processes inside the Ubuntu system. TLDR, this is what I'm gonna do. I'm gonna SSH into the localhost through port 2222. Enter the password, and I'm in. So with this trick, I have both Linux and macOS here, you see? Cool. So my terminal is here in my macOS environment, so it is very fast, normally fast. Here on the side, I have my Ubuntu GUI, as you can see. If I open the terminal and if I start doing stuff, you will see that depending on your system, it feels kind of clunky. You have a little delay when you press the letters. This is not cool. All right, so we are ready to start. Immediately I cd into the desktop and I create a directory that I call fractal. As you can see, I have the side effect also here, right? It's exactly like if I was working here. I cd inside the directory and we're ready to start. So we're gonna clone the link to the minilibX Linux repo. And we're gonna do git clone with this link. Enter. Okay, so now we have the minilibX, we cd inside and we call make. Make is gonna create the actual archive file that we need to compile our application. Now we can check inside and we're gonna see this archive file, libmlx_linux.a. A stands for archive. Basically inside this file I have all the functions compiled, ready to be linked inside my application. Okay, I can go back and we start to code. As you surely know, every application, everything in C starts from the main function. So we are gonna create our file that I call main.c. Here I just wrote a comment in which you have the subject. So you have to create Julia and mandelbrot set. I need to have an infinite zoom, able to take command line arguments, especially for Julia. If you search on Wikipedia, Julia sets, you will see these images here. For example, let's take an instance, this one. Julia set for this complex value. I have -0.8 real and this other imaginary value. Basically, my application has to be able to take at the command line these values. So we will have to create our function alpha to double and render this image, this specific image. Okay, so this is the goal. For mandelbrot, we just don't need this data. So you will see while we are coding this idea. Then I have to have my application listening for events. When I click ask, we have to exit with no leaks. And when I click the X on the window, we have to close with no leaks, of course. I'm gonna write in such a way that makes more sense. It's more intelligible, it's more readable. I don't really care about performance now. I want the code to be just understandable. Maybe I will do a fractal volume 2 in which we are gonna do the bonuses. We're gonna pump our code. We are gonna put some steroids on that. But by now, everything is gonna be just for understanding. Let's start. So I have two kind of prompts. I can have fractal mandelbrot like that, or I can have fractal Julia and the two values, real and imaginary. So real, imaginary, like that. Now the main function has always to be a sort of TLDR of your application. From your main function, I should be able to understand what is going on with your C code. So the main function is a TLDR of your application. So let's try to write it. We start int main, of course, int argument counter, char double star argument vector, because we have to be able to listen to inputs from the command line. Now, given that I have two kind of prompts, I can create some logic into my main that states, well, if the input is correct, we kick in all the machinery. We kick in the MLX connection stuff, the creation of our image, the rendering of the window. On the contrary, we give a string back to the user saying, hey, please feed me with the correct input, and you just exit. So we have this binary logic in my main. I can do if I have these two inputs, right? So I do if argument counter, or better, 2 is equal to argument counter. Here, if you follow me, you know that I like to invert the value and the name of the variable, because it's fairly simple to do this kind of mistake like that. This is an assignment and you can do that. And it's very tricky to find these kind of bugs, especially when your brain is bugged. After hours of coding, you cannot see this stuff. So you do 2 equal argument counter. And here we need to say the input is correct. So I use a string compare. I do fd string compare argument vector in position 1, a string literal, which is mandelbrot. We're going to use all in lowercase just for the sake of simplicity, and 10 for 10 chars. Of course, the string compare is returning me back 0 if the strings are actually equal, right? I made a video already about the string compare, so you can check it out. Given that, I have to invert the logic. If the strings are equal, the return value is going to be 0, namely a false. So I invert to true. Here is written, if I have 2 inputs and the string is actually mandelbrot in lowercase, now we need an OR, a logic OR. Here you do OR, 4 is equal to argument counter, and the same logic as before, right? I just copy this code, and this time I use the string literal Julia and 5 chars. What do you do in this case? Here we have prompt correct, kick off the application. Else, it means that the prompt is not correct, so you simply print a string saying, hey, there is a mistake, please be correct, my friend. So we're gonna do a put string in a specific file descriptor. We're gonna print an error. I'm gonna define that, so I'm gonna do error message. And here I have standard error file number. Okay, we're gonna print in the standard error. Of course, this is to implement. Every time I use these to do's to remember myself, hey, you have to do this stuff later. Okay, to do. We have also to implement string compare, of course, and we simply exit. So we exit with exit failure value. Failure. These are symbolic constants coming from the Unix standard. Now we will create another file containing all the necessary stuff. Okay, this is a basic blueprint of my main function. Basically, we're checking the prompt. If correct, kick in all the stuff. Otherwise, you just go out. Now, let's create our header file. So I go out and I create fractal.h file. In the header file, we put all the other files that we need, all the defines, all the structs, all the prototypes. Basically, we put here all the things that we need in all our files in our application. When we create another file, we use the gars, which are this one. If not def fractal underscore h, you define that. Define fractal underscore h, and at the bottom you do an if. These are called the gars, and they work in such a way that your header file is not included more than once in your files. Okay, we start to include the header file that we need. So we have include standard input output, of course. This is our best friend for debugging, thanks to the printf. Then we include standard library, this for malloc and free. Of course, we're going to include Unix standard. This contains functions such as write and symbolic constants that we need. We can use the math library, so math.h. And of course, we have to include our minilibX. Include the minilibX, we use double quotes because this is not a system library, but is a library which is in our directory. So I do minilibX mlx.h. Okay, we have the header file of our minilibX. Okay, I just create my error message. So I do define error message. And here I have a message like that. You see, please enter this string or this string. There's nothing really fancy to understand. Here I just have escape characters, new line and tab. Here this single backslash is telling this double quote, hey, behave like a char double quote and not like a string double quote. Basically the backslash is removing all the special functions or specific symbols. That's it. We go back in our main function. And here we include, of course, our header file. So include fractal.h. So now, as you can see, I have my error message, my standard error file number, which comes from Unix standard, and exit failure. Now we have these to-dos. We have to implement string compare and to implement put string file descriptor. To do that, we are going to create another file, another module that I call string utils. Here we're going to put all the functions which are processing strings. Every file, of course, I have to include my fractal.h, and we start. So string compare returns me an integer of the string compare. I go relatively fast because, as already mentioned, I made a video about that. So I have char star s1, char star s2, and I have an int n. This is the number of chars we want to check. Every time when we have pointers, it's good practice to check for nulls. So I say if null is equal to s1, or null is equal to s2, or I can have maybe an n which is minor equal to 0. This is of course a stupid input because what's the purpose of calling a string compare with 0 or less? But let's pretend we want to make the function robust. So I say n minor equal than 0. You just return 0. Here you can return, for example, error with the string compare. You can exit. You should handle in your way this function. I would say like that. Of course, I'm gonna use myself string compare, so I know that I will use correctly. Then the actual algorithm. So I'm gonna do while the chars pointed are equal, right? While the chars are equal, so I say at s1 is equal to at s2, and I still have chars to check. So and n is major than 0. And the third important condition, at s1 or s2, here is totally equal, is different from \0. Okay, why is that? Well, it can happen that the strings are actually equal. We reach the \0, which is the sentinel char to say, hey, the string is over. If they are both at 0, this is gonna be true. This can be true if I have more ends to check. And if I don't have this control, the loop will continue, right? We'll go in the following char, which is already outside the boundaries of our strings. So this is an important check. What do we do in this case? We say ++s1 plus plus s2. So we do pointer arithmetic. We are increasing the pointer to the following char. And of course, we decrease n also, the number of chars that we have to check. Okay, that's it. At the bottom, we're going to return at s1 minus at s2. This is subtractions between chars, but chars are basically 1 byte int. So we can do that, of course. So the attention here lies in the fact that when 0, strings are equal. So that's why in my main function, I have this bank that is inverting the logic, right? You understand? Okay, we managed to implement the string compare. Now we are gonna implement the put string. So we have void put str in a specific file descriptor, and we have our string, so s, and the file descriptor. Following the same line of reasoning as before, every time I check for possible corner cases, so I say if null is equal to s, or fd is minor than 0, because file descriptors can only have values from 0 on. What do? You return. You don't do nothing, you just return. And now we implement the actual code. Here I'd like to use recursion just to practice. So I'm gonna do if at s is different from \0. As you probably know, this is redundant code. I don't actually need it, but for readability, we're gonna use it. You can simply use at s, that's the same. You say if the char pointed is not 0, you write it. So you call the write function in a specific file descriptor. Here, the write function, of course, requires a pointer. So we pass directly s and the number of bytes 1. And then very simply, we call again the function. So put string fd, but we have to pass s plus 1, okay? Because we have to move the pointer to the next char. And we use, of course, fd. That's it. So this is my recursion to print a string. Of course, performance-wise, this is not the best. It's just for practice purpose. Recursion. Of course, if you have any doubts related to recursion, I already made a video. Maybe you can check it out, but I think it's not terribly complicated. It's a short recursion. When we do recursion, usually it's good practice to do it only with very short, very easy to read functions, like this one. All right, that's it for my string utils module. We have managed to implement string compare and put string file descriptor. I don't know if there are bugs lurking, but we will see launching the process. Now, to actually use these functions in our application, we have to copy the prototypes in our fractal.h, in our header file. We're going to put all the prototypes. So we're going to do strings utils. And very simply, we're going to pass the actual return value, function name, and the actual inputs. And at the bottom, we're simply appending a semicolon. That's it. This is a prototype. We do the same with put string fd, copy, and we pass here. So what are prototypes? They are basically IOUs to the compiler. To give you a very stupid, shallow explanation. What do I mean by IOUs? You see here in my main function, we start from here, right? So the compiler is going to immediately go in this line and it's going to read this function. It's going to say, hey, what is this stuff? Doesn't know. Having the prototype is going to say, hey, compiler, I know you don't know this stuff, but believe me, I'm going to implement this function somewhere in the code. You will find that, no problem. This is actually how the function is constructed. I have the return type, the name, and the inputs. The compiler needs to know only this stuff. So every time I include fractal.h, at the top, basically, I'm passing all these prototypes that the compiler needs to know. Now, this is a very superficial explanation, my friend. Dig down by yourself. Okay, now you can see that I can use my string compare very easily. I don't get the mistake. And I cancel my to do. Now I just need to use a curly brace. Here I have a mistake. I wrote put r, I need put string fd. And that's it. Now it works. We already have a minimum viable application. Let's try to launch it and let's check if it works. So this is the compilation that we have to do. Basically, we have to link the minilibX Linux. This upper level is telling this is the path to the minilibX. Indeed, this is in the same directory. This little L is telling me the name of the actual library. So it's going to be minilibX Linux. and these are just other stuff that I just copied from the documentation. I already explained in the MLX video the stuff, so I just compile. Let's try if it works. Okay, it compiles, so I have my fractal application. I do fractal mandelbrot with many T's. Let's see, what do we get? You see that we get the correct input we want to get. I just need a new line because this is done by fish. So let's go on my fractal.h and let's put here a new line like that. Okay, let's save, compile, launch. Okay, it works. And of course I get the return value, which is 1 exit failure. Let's keep going on. Now, keeping on with the concept that this is a TLDR, right? Let's write what I want to do. I want a big function that kicks in all the connection, the hooks, and the data of my fractal. What do I mean by that? Now I show you a slide that I prepared so you can understand better what I imply. So as explained in the beginning of the video in my little 20-minute theory explanation, you understand that the mandelbrot set is a collection of complex numbers, right? These complex numbers are just composed, indeed. That's why they're complex. They're composed of stuff. We have real parts and imaginary parts that for us will be just coordinates in a 2D Pythagorean plane. What I want to do is create a struct that contains all the data related to the fractal. We can say that I create a fractal ID in which we have everything that we need to render a fractal. So inside we will find all the stuff related to the MLX connection. We will find an image because, as explained in my MLX video, we're gonna manipulate images. Indeed, we are gonna have a window and we are gonna buffer our pixel in an image object. Only when the image is ready, we're gonna push in our window. This increases drastically the quality of the code. Namely, we are not gonna use MLX pixel put. We're gonna use my pixel put. Again, just check the section of my video about MLX to understand this point. And of course, we're gonna have all the hook values. For example, we're gonna have zoom, shift, the amount of iterations that we're gonna do with the function, and so forth. So I'm gonna create this struct that contains all the necessary data. So let's do that. I'm gonna go in my fractal.h, and here we are gonna create our fractal ID, if you want. It's like an identity card with all the stuff in which we have MLX stuff, an image, which is just another struct, and hooks values. Okay, let's start. So we do typedef, struct fractal. Inside we put void star MLX connection. This is a pointer coming from MLX init, right? Then another pointer coming from MLX new window. Basically I have MLX window, I call MLX new window. Then we need our buffer image, our struct. All this stuff, my friend, comes just from the documentation. It's not that I have this super knowledge, super understanding of what is going on. I just read the documentation and here you can find all the things you need. Indeed, this is an image. These are the values coming back from a function which is get data address. So basically we have to create this. I recall to you the amazing principle RTFM that we programmers need to know very well. Okay, let's create our image struct. Image, this is basically a pixels buffer, if you want. We're gonna use this, fill with all the pixel, and then push in our window. Okay, so again, typedef, struct image. I do like that. And inside we put our values coming from MLX get data address, I guess it's called. MLX get data address. Yes, is this function here. Only written in this fashion. Okay, so I have a void pointer. This I call image pointer. This is a pointer to image struct. Here we have another pointer which is very, very important, which is pixels pointer. This is the actual pointer that we're going to use to change the pixels in our image. It's pretty important. Points to the actual pixels. As you can see, we have a char star. This pointer is pointing to 1 byte. Okay, then we have int bits per pixel. We can do BPP. This is self-explanatory, right? How many bits we have in a pixel. A pixel is an integer, so we have 32, the value here. should be, right? Allegedly, depending on the system. But and we have endian. We don't really need this value. And then we have another value which is important, line len. We are gonna use it in myPixelPut function. Okay, type image. So coming back to our fractal, we are gonna put here the image. So type image, image, our little buffer. Okay, now we still need variables, or better, member variables, because we are inside the struct. We will do them as long as we are coding, so we can understand like all the pieces fits into this puzzle. Okay, now we have type fractal, which is the actual new data type that we're going to use thanks to the typedef. Okay, here just leave a to do. We're ready. So go back here, and at the very top, I'm going to declare a fractal struct. So type fractal that I call fractal. Now we have this ID, we have the struct. We kick in all the MLX machinery, so all the function MLX init, MLX new window, MLX new image, and so forth. Essentially connecting to the X server and starting the process. So our TLDR. First point, we can call the function fractal init, and we give as an input our fractal. So fractal, of course, we pass it by reference. We're gonna pass a pointer to this struct that contains a lot of stuff. And the second point can be a function like the actual rendering on the window of the fractal. So I call a fractal render. Again, I pass my fractal pointer to that. And at the end, so I have the fractal which is rendered on the screen. At the end, I just leave control to the server, and I kick in a MLX loop, passing a connection to the actual server. So I do fractal dot accessing the member variable MLX connection. So basically, this is a loop event, listening for events like clicking the mouse, clicking on a key. Of course, we have to implement all of this stuff. We have to implement all of these hooks. But basically, my main, as you can see, it's kind of ITLDR. If the prompt is correct, what do? You have a fractal, you init all the data, you render, and then you keep listening. You see? On the contrary, you just prompt the user to give a correct input. Okay, let's save this. And we have to do the fractal init function. We're going to do another model. I'm going to do vim init.c. Usual pattern, we're going to include our fractal.h, and we start. This will init MLX, listening events, and hooks data. Okay, so my init function doesn't return anything, so it's going to be void fractal init, and we have as an input only a pointer to our fractal. You see how cool is that, to have a struct that very compactly contains all the variables that we need to manipulate in order to do stuff. That's very handy, right? And passing by reference is efficient because I don't have to copy all the stuff in the next frame, right? In the fractal init frame. So here we kick in the MLX stuff. I already explained this stuff in the MLX video, so I hope you know everything I'm gonna do. So I do fractal. I access with the arrow operator, right? Because this is a pointer. MLX connection is equal to MLX init. Boom. I need to do all the necessary evil controls. So I do if null is equal to fractal MLX connection. We're going to create a function that I call malloc header. Okay, that we have to do. Okay, now we create the window. So fractal MLX window is equal to MLX new window. And we pass all the necessary data. So fractal MLX connection. Then we have here two parameters, which are size X and size Y. So to do this once, we're going to use defines. So I go back in my header file, and here I define width of my window, which is 800. Let's do that. And I'm going to define height 800 as well. We use a square to keep the math simple, the rendering math simple. You will see. So it's kind of redundant to use two symbolic representations, given that the value is going to be the same, but I think for clarity, for understanding the overall code, it's good. So we go back to init, and here we're going to use our symbolic representation, which are width Y, of course, is the height. Here we have char title, which is the thing we want to be reading in our window. So here we do something. We go back to our fractal.h, and we put inside our struct another member variable, which is char star name. This is going to be the actual name of the fractal. I save it. I go back to my main, and you already understood what we're going to do, right? Here at the top, I just very simply say fractal point name is equal to argument vector in position 1. So in my struct, I have the actual name of the fractal, which is mandelbrot or Julia. Cool. Now we go back to init, and here we are going to use exactly that member variable. So I do fractal, here I use the arrow, and I use name. That's it. So we have managed to create our window, which is just a square, 800 per 800 pixels. Now, the usually necessary evil controls. I say if null is equal to fractal MLX window. What do you do? Well, here I have more operations to do. I'm gonna destroy the display. So MLX, destroy display, because in my MLX init, a display is gonna be created, which is just another struct. Again, back to my MLX video. And I pass as an input fractal MLX connection. Then I have to free the MLX connection, so fractal MLX connection. And then again, I'm gonna just call my function malloc error. Okay, good. We have established the connection with the server. We have created a window. Now we have to create our image. So I do fractal error image point image pointer. I do MLX new image. I pass the inputs, so the pointer to the connection. Say this is a boring task, and then you have width and height. So we're gonna use exactly the same parameters as the window, because we want the image to be the same size as the window for the reasons you already understand, right? We have the image and then we're gonna push inside our window. Here we use height. Okay, so we have our image. Again, necessary controls do. So if the pointer is null, we just copy this code. We just have to add MLX destroy window, okay? And we pass the relative input MLX connection and MLX window. Okay, we already have a lot of stuff here. Now, of this image that we have created, we have to get the data, right? We have to get the data, and we have that special function get data address. That function is returning me the pointer to the actual pixels. This is the most important piece of data that we need. So we're gonna do fractal image pixels pointer is equal to MLX get data address, and I pass the data, so a pointer to the image, fractal image pointer. And then look here, I have bits per pixels, size line, and endian, but they are all pointers, as you can see. So I have to pass them by reference. Let's do that. So fractal image bits per pixel, and here I just put an ampersand. So I'm gonna pass a pointer to this member variable. I don't need to use parentheses here because these kind of operators have associativity, which is from right to left. Here we have size line. We do the same things, so I'm gonna go fast. Line len, size line, it's the same. Address, fractal image endian. We don't really use this endian, but we have to do that. Okay, we have all the piece of data that we need. At the bottom, we still have to call the function, I don't know, hooks init, hooks or events, event init. Basically, we're gonna call the function an MLX hook that is gonna listen for specific events. So this is a to-do. Of course, as an input, it's gonna take the actual fractal, pointer to the fractal. You see, a useful is to have only one big struct containing all the things I need. And data init fractal. Data init is gonna contain all the zoom, shift, iterations kind of data. Okay, now we have the image with all the controls. We have to create this malloc error function. We're gonna do here. So I have a void, malloc error, no input, so void, and we say I can use the print error function, problems with malloc. So this p error is gonna print this string, problems with malloc, plus the actual error that happened, thanks to the error no global variable. These are details you don't need to know. And then we just exit, right? Exit failure. Here, given that this function is only used inside this file, inside this module, I can use this keyword, static. Static used here means, hey, this function is only for this file. I don't have to use in other file projects. So, long story short, I don't need the prototype to be in my header file. I don't need it. It's only for this file. So I would argue that this keyword, if you know what it means, makes the code more readable. You immediately see this function and you say, this is something related only to this module. Okay, we have everything we need. We have the connection, we have the window, we have the image and the relative data that we can manipulate. Now let's try to compile. Let's check for eventual bugs. Implicit declaration of function. You see, I get this problem because in my init function here, I need to copy the prototype into my fractal.h. So let's do that. Init. Here it comes. Now I have the prototype here. Perfect. I save, I go out. Let's try to compile again. What is this? Fractal render in main. Of course, I had to comment, but it's fine. Of course, the compiler doesn't know what is this fractal render. Let's compile again. Okay, it compiled. So by now we are on the right track. Now my fractal init is correct. Let's go to the actual fractal render function. So we create another module that I call render.c. The usual pattern, we include our header file. So fractal, now here I got it wrong, fractal.h. And this is the actual meat of the code. Because we have to check if a point is a mandelbrot or not. We're going to use the same code, both for mandelbrot and Julia. You will see that we have just to tweak a little bit the code. So now we talk pixels. We have to actually manipulate the pixels in our image. Void fractal render. As the input, I have a pointer to my struct. So fractal. Perfect. So I have my actual image, right? See, you have the image, which is 800 pixel width and 800 in height, correct? What we are going to do is take all the pixels coming from the image. So all the pixel in the first row, of course, this is no scale, but just to get the point across, and check if they are in the mandelbrot set. Of course, we have to apply some math. We have to rescale everything. I don't want to work with integers. I don't want to work with the size. You will see. But let's start with the actual pixels. So I do int x and int y. Okay, and I just have to do a nested while loop to check all the actual pixels from 0 to 799. So let's do like that. I do y is equal to -1. Let's do, and I do while prefix increment y is minor than y is the height. So let's do that. Now we nest a while loop. So while x that we have to put here, x same pattern -1. So plus plus x is minor than width. So effectively we are checking all the coordinates, right, in our 2D plane. And here I can call a function that I call handle pixel. Handle pixel. Well, handle coordinate, but handle pixel. Let's do handle pixel. So x, y, and the struct. So fractal. That's it. Okay, this function is going to pass all the x and y coordinates to my handle pixel function. Here, let's implement here. So void handle pixel. We have int x into y and a pointer to the fractal. Okay, here is where all the magic is going to happen. And to do the magic, we have to make a change. First change that we have to do. So first thing, I have to do this transformation. You see, I have my image, which has this 800 pixel, but I don't want to work with values which are 0, 1, 2, 3, 4, 5, 6, 7 integers. I want to work, first of all, with reals and in a specific range. Why is that? Well, here I have prepared just a stupid slide to make the point clearer. As you can see, the mandelbrot set is this object in a specific range. In a specific range, just look at the coordinates. We can say that in the x real coordinates, we have a range from -2 to 0.5. In the y coordinates, in the imaginary axis, we have -1 plus 1. Inside this rectangle, we have the mandelbrot set values, which are real values. So if I use the coordinates values coming from my image, x and y, 0, 799, I'm not using effectively the actual points that can live inside the mandelbrot set. I don't see anything. I don't even see the little s of the mandelbrot set, right? I need to transform the coordinates. I need to transform that. Effectively, I have to change the coordinate system. I have to map to scale from 0 to 799 to -2 plus 2. Of course, the vast majority of points live in the negative side of the plane. So I need to do that. Now, I hope my point is clear. I want to have these -1, -0.8, -0.6, and all these values here. I don't really care about 1, 2, 3, 5, 8, 786. Basically, if I work at the scale of my pixels, I have this square here, you see? And the mandelbrot set is this tiny thing here, which lives in those values here. I'm sure you understand what I'm saying. Okay, the actual code. Here in Stack Overflow, we have the answer to this riddle. Indeed, we have how to scale down a range of numbers with the known min and max value. And here you have the mathematical formula. Basically, we have this function here in JavaScript, scale between. Let's try a piece of code to check if this is what we want. So here in this piece of code, I simply plugged the values from Stack Overflow. This is the mathematical formula that we're going to use. And this is a for loop that is looping from 0 to 799 and is scaling those values in the range -2 plus 2, exactly what I want. Let's try to launch, run map function. And here is the result. Basically, 0 became -2. Then we have all the values in the middle, and 799 is +2. So you see, we took some values and mapped into another specific value, and this specific value is respecting the proportions. So you see, let's try another scale. Let's say at school you have grades that are from 0 to 10, while on university in Italy we have from 0 to 30. Here we put 10 this time, we run it, and we get that 6 in school is equal to 18 in university. The 9 is 27, of course, the 10 is 30, okay? So you get this mapping. These are school, Italy grades to university. So I hope you understand this map function, how it works. Basically, is scaling some values, maintaining the relative proportions. Cool. So we're gonna simply copy this function here, and we're gonna plug in our project, but in a new file. So I'm gonna create a new file that I call mathutils. Same pattern, we include fractal.h, and here we copy our function that I want to call map, like more map. So this will allow us to go from this to this, okay? Pay attention that here we have 5 inputs, but the Norminet won't allow that. If you want to copy past, you can assume that the old min is 0, so you can forget about this old value. Engineer by yourself the actual solution. This is just for overall principles, for overall ideas. Okay, now as always, I have to copy this inside my fractal.h. Same pattern at the bottom, we do math. Here comes the long prototype. This, by the way, I think it's called linear interpolation if you want the nerdy nomenclature. Linear interpolation. Okay, now we can go back in our render function. So this problem is fixed with the map. The actual function to check if a point is in the mandelbrot set, you know from the theory part, is z equals z squared plus c, where both are complex numbers. Z initially is 0, namely 0, 0, and c is the actual pixel, is the actual point. Okay, so now I will create a struct in my fractal.h, which is the actual complex number. Let's do that. Complex value. So usual pattern, typedef, struct complex, and inside I only have 2 member variables, which are a double. This is the real component, but I will call it x for simplicity. Of course, this is real, and this is gonna be the imaginary component of our complex value. But in our case, for our purposes, this is just a y coordinate in a 2D Cartesian plane. and here I do type complex. All right, cool. I have my struct, and yeah, now we can use in our render function. So I go here, I declare to complex, type complex, I call z, type complex c. This of course is true for mandelbrot. So z, we said that initially zx is equal to 0. Of course this is a double, but just for clarity let's do that. And zy is equal to 0.0. First iteration. On the contrary, c is the actual point that we want to check. So we have to take our x and y coordinates and transform them with the map function. I'm gonna do I'm gonna do c x is equal to map and scale value the x, so a value ranging from 0 to 799. The new mean is gonna be -2, new max is gonna be +2. Old mean is 0, old max is 799. We do the same for the y, so I replace this, I replace with y. We're of course not 799 hard coding these magic numbers, but I should use width and height. Okay, so if you change the defines of the constant, everything will change. Other mistake that I can see, yes, is this one. Indeed, y starts with the plus and minus. You understand why? Let's try to get the point here. So effectively here, what I'm doing with my function, I'm scaling down my x and y image coordinates into some real values that I can use. My new image has this size, right? Is this size here, -2 + 2. And 0x has to be mapped to -2 here, right? But 0y has to be mapped not to -2, but to +2, right? We start from here. See the catch? Y has to be positive upstairs and negative downstairs. So it's reversed. Of course, mandelbrot is a symmetric object, so the thing will work the same, but this is not correct. Okay, I think we are okay here. Now, this is the pixel coordinates x and y scaled to fit mandel needs. Now I have to make the iteration, right? I have to iterate these numbers to check if they escape to infinity or they stay bounded. So what do? I say while something, and now we understand, until that condition. So this is basically how many times you want to iterate the z function, z squared plus c. You want to iterate z squared plus c to check if the point escaped. So that's the condition I want to put here. Then we have to implement the function, right? So actual z squared plus c. Okay, so I want to write here exactly like the function. Just I want to make a parallel code function. So I want z equal z squared plus c. I will write z is equal to z squared. I can do square complex. I pass as an input z. Then I have to sum c, and I do sum complex, square complex, and comma c. Okay, so these are two complex math functions that we have to implement substantially. Then we have the control. If, again, something happens, namely if the value is escaped, is the value escaped? If the value is escaped, you are gonna put a pixel of a specific color. So I'm gonna do my pixel put. This we'll have to implement. So my pixel put, we'll leave it with a to do. And you just return, because you don't need anymore to do anything, right? You put the pixel and you pass to the other pixel and you check. Okay, let's stay like that and let's understand point by point what we have to do. So first of all, I would start by the formula, sum complex and square complex. So we go in our file, math utils, and we implement these functions. So sum complex is vector addition. So you just simply sum the real and imaginary components, so x and y. Let's do that. So type complex, sum complex I take two complex numbers that I call z1, second complex z2. Z, as I understand, is usually used as a name for complex stuff. You immediately understand that this is complex math and not regular math, okay, as I understand, but I'm not sure. Here we say it's a complex result. This is the final result that we will return back. We just perform now addition of the same members. So I say result x is equal to z1 x plus, here I just wrong, z1 plus z2 x. As easy as that. I copy this, y is equal to z1 y, z2 y, and then I simply return the result. Boom, it's done. As you can see, it's basically vector addition. I just sum the same components. Okay, for the sum it's super easy. Squaring is trickier. Square is trickier. Okay. So the usual boilerplate, type complex, square complex, and I have a number, so type complex z. Now I already explained this idea in the introductory part. Let's just refresh our memory. So I created this simple slide in which I have a complex number squared. So I have x real. Of course, I use x because we have a parallel between x coordinate and real values. Y imaginary. So I square it. What is going to happen? Well, this is actually what is happening. We do algebraical processing, so we get this. It's squared plus xy I plus xy I plus this strange number, which is I squared. And the thing that we have to know from complex math is that I squared is equal minus 1. That's the only thing we have to know. So I get it squared plus 2xy I minus y squared. And what does it mean? Well, it means that we have the squared new complex number, which is composed of a real part and an imaginary part, you see? To get the square real part, you need to make the subtraction between it squared and y squared. To get the imaginary part of the complex squared value, you use 2xy. That's it. Let's apply this in code. So real is equal to it squared minus y squared. Imaginary is equal to 2 per x per y. Same pattern as before, type complex, result, and we say result real or x is equal to it squared plus y squared. So zx per zx minus zy per zy. Okay, that's it. On the contrary, result y is equal to 2 per zx per zy. Okay, at the end we just return result. And that's basically it, allegedly, right? It should work as expected. So we have this square complex that is performing these transformations. This is a formula that it's easy to derive, as you saw, and that's it. Now, as usual, we have to copy these prototypes in my header file. Let's do that. So we copy here, square the square complex. We go here, we paste. We're done. Okay, we go back to our render. And now we have done this first point, okay? So we have implemented these two functions. Of course, this is not good practice to have functions inside loops, but for simplicity's sake, I think it's cool. Now we have to understand, is the actual value escaped? How do I understand this point? Well, we know that inside the mandelbrot set, we have all the points that stay bounded, right? They move only inside these frames when iterated in with our function. On the contrary, outside, the points escape toward infinity. So how can I say that a point is outside the mandelbrot set? For example, how can I say that this point minus 0.6078 is outside the mandelbrot set? Well, we are going to exploit the actual vectors to see if a value is outside. Now, to do that, we are going to use the Pythagorean theorem. Because you see, every point has two specific vectors. If you see here, we have this and this other one. So every point can be described as just these two vectors. Now, thanks to this, we can find very easily the hypotenuse, right? This green line. And that's what we are going to exploit. It's very easy to calculate, and let's try to understand how I want to exploit it. So here I have, for example, hypotenuse 1 as a size. So here you can see the actual hypotenuse, which I made in one upstairs and one downstairs just to check this. As you can see, if I rotate this hypotenuse, I still have some points which are inside the mandelbrot set. Just look at the x-axis. you can see that I still have points ranging from -1 to -2 in the x-axis. So I say if the point creates an hypotenuse which has size 1, it doesn't mean that the point has escaped. I'm not sure still. You see the catch? Let's try with a bigger hypotenuse. So now we're going to use an hypotenuse which has size 2. So if I rotate this big boy, you can see that allegedly we already have all the points inside the mandelbrot set. You see, I can assume that the point has escaped. So Pythagorean theorem, here I would say if hypotenuse major than 2, I assume the point has escaped. Fair enough. So let's calculate first of all the hypotenuse here. How do I do that? Well, I have to sum the square of the coordinates. Squaring this value, I get the cool side effect that if I square a negative number, it's gonna nonetheless become positive. So I don't need to worry about the sign of these values. So I say zx per zx plus zy per zy gives me back, following the formula, what do I have? I have c squared. I'm gonna square the actual c. So my c is 2, I'm gonna say it is 4. So here I'm gonna do something. I'm gonna do, let's go back to our fractal.h, and here we put inside our struct some hook variables, you see. This is gonna be a value that we can change. So I say double, this I'm gonna call escape value. So when the point reaches escape velocity, of course we know that this is just our hypotenuse in our mind, okay? Escape value. So now we have to go back into the init and we start to populate all this data. Data init, this function here, we start to call it. So we go here and we do data init. As usual, void data init pointer to our fractal, like that, fractal. And we say fractal escape value is equal to 4, right? This is, of course, 2 squared, my hypotenuse. Go back to our render file. So here I say if this value is major than our escape value, I assume the point has escaped. Okay, let's save it. Now, what is this condition here at the top? While what? Again, this is how many times I want to iterate my function until I reach escape velocity. So in my mandelbrot set, there are points that require many iterations before escaping the set, right? For example, in this little island of the mandelbrot, I have to go here. And here, the points which are really close to the mandelbrot set require many iterations before escaping. You see? So many iterations, we have to perform the function. Of course, the amount of iterations that we are gonna do is gonna imply the refinement, the definition of our mandelbrot set. The more iterations, the more clean is the image. So let's go here. Go to mandelbrot set explorer, and you see that here we have a lever that we can use. It is basically the amount of iterations that we are gonna perform. Let's watch what happens if I change the amount of iterations. Here I have a little island, and here I get many iterations. Let's decrease a lot. Let's go to 30, 20. You see how bad the image is, depending on the amount of iterations that we are gonna do with the function. Because these points at the margin, the deeper you go, the more iterations you need to understand if the point is in the mandelbrot set. Now I turn on these iterations, you can see that the image becomes clearer and clearer, more refined and more beautiful. So I can zoom in. You can see even if I zoom in a lot, I still see pretty well all the points. Of course, we are gonna need a lot of calculations, especially when we go that little. Here I'm gonna increase again. I'm gonna go to the maximum, for example, 1500. This requires a lot of calculation to render, but the quality is pretty impressive, you see. Just look here at the real and imaginary values. As I move the mouse, these are essentially the same points. We have a very little change of these points. Now let's go with very little iterations. See, I don't see anything basically. I don't see anything. If I do 46 iterations, basically I don't see anything. Let's do 130, nothing. Only when I get to 200 and something, I start to see stuff. So this is exactly our while loop. that we're doing now. So here I'm saying how many iterations I want to do. And this is a good candidate for being a value that we put inside our hook member variables. So we do, this is an integer, and I can call it iterations definition, because this is highly tied value tied with the image quality and speed and the rendering speed. Okay, I save, and in our init file, in our data init, we say fractal iteration definition is equal to, let's start from 42, totally arbitrary number. Basically, we're saying this, I want 42 here. I should be able to see an image like that. Okay, let's go back and go back to render. Here I need an iterator that I call I. Of course, every time we have to initialize our I to 0. And we say while I is minor than fractal iterations definition, you keep doing your function and you check if the specific point that you get is outside the boundaries. If it is, you put that pixel. Otherwise, if we get here, it means that we are in mandelbrot set, right? We are in mandelbrot given the iterations made. So now we do something cool. We are gonna say here integer color, because at the end of the day, a color is just an integer, RGB encoding, right? So here we say color is equal to what? Here we're gonna use again our map function. I'm gonna do map, and the value we're gonna use is gonna be I. So the number of iterations. Then we simply put the new mean. The new mean is gonna be, for making all the colors, we want something that ranges from 0 to 0x ff, right, in hexadecimal. So here I can say from black to white. Basically, black is the absence of colors, white is the concoction of all the colors. But when you see white, indeed, you're seeing a concoction of all the colors. Old mean, old max. Old mean is 0, and max is fractal iteration definition, right? Is 42 in our case. Okay, I need some defined colors. Let's do that. To do these tedious tasks, ChatGPT is our go-to place. Of course, I'm not going to write all the defines. So, okay, here we come. So I have ChatGPT that is working for us. Amazing, this artificial intelligence stuff is, wow. So I said, make me some psychedelics ones, which is pretty cool for fractals. All right, I just copy, and we go back in our header file here, fractal.h, and we simply passed all these colors. Boom, perfect. Now we have access to all of this. Let's go back. Okay, we're almost ready with our handle pixel function. Now we have to code my pixel put. Okay, we're gonna put here just above. This is gonna be a function. I'm gonna write this function very fast because I already explained in MLX. You can just check the pixel put part. So put a pixel in my image buffer. And we do static, because this is gonna be a functional here, void my pixel put. I have int x, int y, pointer to our fractal. Or better, here I can simply say type image. So I'm gonna be a pointer to my image. And the actual color. So going very fast, I have the offset. The offset is given by y per image line length plus x, which is multiplied by image bits per pixel divided by the size of a byte. So it's going to be 8. That's it. So we have to calculate where exactly is the pixel that I want to color in my grid. Again, all of these ideas are in the previous video. So now I'm cast to an unsigned int pointer. An int is basically a pixel, and I do image pixels pointer plus offset. This is pointer arithmetic, so I'm gonna add the offset to the actual pointer to pixels. Here I say is equal to color, and here I just have to do reference. Okay, this is my pixel put. Now let's go back to my pixel put here, and we pass the actual inputs that we just made. I use x and y. I'm not using the change values, right, coming from the map function. I hope you understand the point. The image is still my 800 pixels, so I have the same coordinates. I'm just faking that these points have a specific value thanks to the map function. But at the end of the day, I have to render into that image. So here with my pixel put, I have to use X and Y. A pointer to the image, so I have fractal image, pass by reference, and then the actual color. So a color is gonna be a cool mapping depending on the iterations, you see. I have a range which comes from black to white, so all the colors. 42 iterations is gonna be white, 0 iterations is gonna be black. Okay, iteration definition, we return. Of course, I have to increase I, given that this is a loop. If I go here, I do my pixel put, again, X and Y, fractal image by reference. And if the point is in the mandelbrot set, we're gonna use, which color we're gonna use? I don't wanna be black like it should be, I wanna be lime shock or psychedelic purple. Okay, render, let's do that, psychedelic purple. Okay, we're done. So let's check again. I get the point here in my C. Okay, seems like we are correct. Okay, at the end, we just need to, in my fractal render here, of course, I can use the word static again, because this is gonna be used. And I put here, we have the image, which is ready. We have to push inside the window. So we're gonna do MLX, put image to window, and we pass the inputs. So fractal, let's connection, we pass the window, pointer to the image. Then we have these X and Y, they're simply the offset related to the window. Given that you have the image which is exactly the same size as the window, and I don't want to offset anything, okay? I think we are almost ready. Now we have to just check for details. Okay, this file seems correct. Let's go back in the main. I have to uncomment my fractal render, and like always, I have to put inside my header. So handle pixel, we go in the header and we put just beneath the init render. Okay, let's save this. Let's check again the main. Now should be okay, no problem. Here everything seems okay. Math utils, the render file, which is the most important. String utils, the init. Let's check data init. Let's remove this to do, and everything's incorrect. Okay, let's try to compile. Let's check what is going to happen. So I compile, and it compiles fine. Now let's check the actual result. So of course we're gonna run our application here inside the Ubuntu machine. Fractal. Let's try fractal mandelbrot. Okay, here we are, my friend. As you can see, we have our mandelbrot set. Of course, everything is purple, but we can change very easily this color, right? As you understand. Let's close it. Here I can do, for example, let's do it just simply white. I think even white is kind of cool. White, save. I compile, fractal mandelbrot, boom, here we are. Now, of course, I cannot do anything with it. I need to kick in all the events, and we will be able to do movements, zoom, for example. Okay, this is the blueprint of the rendering of the mandelbrot set. Now we're gonna make the program interactive. All right, let's start. So we go into my init file, and here we uncomment our events init. And now we're gonna populate with the events that we wanna listen to. So data init, just here, I'm gonna do void events init, and I have a pointer to our fractal. Okay, of course I can do my static keyword to make the code more readable. Static. So for events, my friend, you just simply follow the documentation. Everything is written here. We're gonna use this function MLX hook. Okay, so we have to say MLX hook. We pass the necessary elements, so it's gonna be the window, MLX window. Here we have the X event. So for the X event, I want the key press, and for the mask, as you can see, it's gonna be exactly the same, only adding mask at the bottom. So key press mask. Then I have a pointer to a function. I'm gonna say key handle, and here I can pass directly my fractal. So here I have to do. Okay, with this function, basically I said, listen to all the key presses. Every time I press a key on the keyboard, this is gonna be listened, and a key handle function is gonna be sparked. let's do the same with the mouse. So the pattern is the same. I'm gonna just copy this and I'm gonna paste here. For the mouse, I have button press here. So I'm gonna do that. Button press and button press mask. Okay, let's do the last one for now, which is destroy notify. This is basically when you click the X in the window to close. So I copy this and I pass here, destroy notify. The actual mask is this one, structure notify mask. Okay, here we change, of course, the name of the functions. Here I have a key handle, let's call mouse handle. And here I call it close handler. Let's put the R handler. All right, so what happened here? Basically, with this function, I turned on all the events. Now my process is listening to this kind of event: key press, mouse press, and when I click the X in the window. Of course, we have to implement all the handler functions. So key handler, mouse handler, close handler. So we do another module that I call events.c, the usual include of the fractal.h, and we implement all the functions. So as written in the documentation, every event has its own specific prototype function, okay? So for key down, namely key press, I can use this specific prototype. Okay, so it's gonna be int key handler, and int here is gonna be key, no key code, but key sim. This was a conundrum that I quite didn't understand. I explained this in MLX, in the MLX video. Maybe you can check it out. And here I have a pointer to my fractal. Okay, let's start to do stuff. Here, first of all, I'm going to show you what is going to happen in this function. Say %d key sim. So as you can see, printing the key that has been pressed. So let's go back to init. We're gonna comment all of them. So you can understand the basic principle here of this MLX hook. Cool. Now we go back to events.c. We copy the prototype like always, and we put in our header file. And the same thing as always, you know super well by now. Hooks, events, and I passed the prototype. Okay, now we're ready. We are gonna compile. Here I have undefined key press and key press mask. Oh yeah, of course I have to include on the file that contains those symbols. So it's gonna be include x11 x.h. Perfect. Let's try again. Okay, now it works. Let's go back in our virtual machine and let's launch mandelbrot and let's do something. Now I press some random keys. See what is going to happen? I get a reaction. My program is listening to this stuff. You see? I press ask, for example, I get this number. So we can do something with that. Okay, let's close. Let's go back in our events.c. So here simply I say the pattern is simple. If the key is that, you do that. If the key is that, you do that, and so forth. So we can respond to specific keys in a specific fashion. Here I say if, I don't know, ksim is equal to, here we're gonna use symbols which come from this file, which is x11 ksim. For example, you have escape, which is exactly this. You saw before the number, right? This is in hexadecimal, but we're gonna use this symbol. It's k escape. It's making the code more readable and more portable. So let's do that. It's k underscore escape. So this is when I press ask. When I press ask, I want to close the window in a clean way. So here I can do in my events function. In my init, I have that the struct fly. I call the function close handler. I want to use the same function for ask. So I'm gonna do that. I'm gonna call close handler. Close handler. And of course, it takes as an input the fractal. Okay, to do. Then else if. And here the pattern is self-similar. So I'm gonna say if we press the arrows, you're gonna move the mandelbrot. And if we press here, I can also add plus or minus for the iterations. So the actual definition. So now I'm gonna write that. Okay, so I've added all these elements, left, right, up and down. These are the arrows, plus and minus. So for the plus and minus, I want to do fractal iteration definitions, right? If it is plus, I'm gonna do plus equal 10. So I'm gonna increase by 10 the actual iterations. I copy these and I do the same for the minus, namely the same in reverse, minus equal 10. So these are the bottom plus and minus that are doing exactly this. You see, I change iterations. Here in my application, I press plus and minus. That's it. But that's the same idea. Then here we have to understand how the shift works, right? We have to understand how to shift the image. Now, I'm going to show you 2 slides that I've made to make this super easy. So let's start from the shift left operation. We have our image that has been resized thanks to the map function. And let's try to do something. I want to shift a little bit to the left of the image. So what do? Well, I can add 0.5, which is just an arbitrary shift, to my range, right? So effectively, the result is going to be that I have a new range that is minus 1.5 plus 2.5, you see? So let's change this range to the new range. What is going to happen? Well, just check the points inside the mandelbrot set. So the image has to shift to the left accordingly. It has to match the minus 1.5, effectively getting a shift of the same size of the arrow, you see? So increasing the X range counterintuitively, because you think that if I add something, the pixels are going to move on the right. I get a shift left. Let's try to apply this in code. So left here, first of all, let's go to the render. And here in my transformation, in my map transformation, CX, you are gonna add this shift. So fractal and this shift value that now we have to create. So let's go back in our init, or better in our fractal.h, and let's put this new value in our hook members. We call it double shift x double shift y. Okay. Now we go back to our init, and in our data init we say that fractal shift x is equal to 0. We start from 0. Shift y again is equal to 0, 0. Cool. Now in my render, let's go back. We perform this transformation. The transformation is that when I map the values from a range to the other, I have to add this fractal x shift x, and here I have to add fractal shift y. Okay, let's go back to my events.c. Now if I want to go to the left, what I'm gonna do, I'm gonna say fractal shift x. So I want to shift to the left. You just saw that I have to increase, right? I'm gonna increase 0.5, let's say. Here on the right, I'm gonna do the opposite. So, and by now, let's try only that. So let's comment here. Okay, by now I have only left and right arrows. And of course, at the end of my key handler, I have to call again the render function, because I have to re-render the new frame. So render fractal render, and I pass the fractal. This is like a refresh the image. Okay, it should be correct. Let's try. Here I have this mistake. It's k left, it's k right, probably because here in my header I have to add include x11 ksim.h. Let's try now. Okay, it works. Let's try it out. So I launch my mandelbrot. If I press if there is a bug, what is happening? Let's watch again. Yeah, of course I used the same operation here. Here I should use minus. Okay, let's try now. So let's compile and launch. And we see that the image is moving accordingly, right? Left, right, left, right. It seems like it's working properly. So we go in our event page, following the same line of reasoning. Key up is gonna be minus, and key down is gonna be plus. Okay, let's try. So I'm gonna compile, launch. Oh, what an idiot, I had to change. My brain starts to cripple. It's like 3 hours of code now. Okay, we go back to events. Of course, here I have to use y and y. Okay, compile. Okay, now we're able to move our mandelbrot set inside our terminal with the arrows, you see? Up, down, left, and right. So we got the actual behavior that we want. Now let's implement this close handler. We're gonna implement here directly. So void close handler, and we take as an input a pointer to our fractal. Here very simply we have to and destroy everything. We do minilibX destroy. We start from the image and we say all the necessary data. MinilibX connection and the pointer to the image. So image pointer. Then minilibX destroy window and the data. So minilibX connection and the window. Then minilibX destroy display. Okay. Fractal minilibX connection. Then we free the minilibX connection and we exit. With exit success. Boom. This is our close handler function. I want to spark this when ask or I press the X in the window. Okay. Say I take this and I bring in my header file prototypes. Perfect. Let's go back in our events. So now I uncomment this. We go to init and we uncomment this destroy notify. Let's see if this works. I don't have close handler. Why? Compatible function pointer. On destroy wants this prototype, so we have to change it. So let's go back to events. My close handler, I need to have this prototype, so we change it very simply to int. And of course we have to change also in our header at the bottom. We put int. Okay, we should be okay like that. Let's try to compile. It works. Let's launch again. Mandelbrot. I press the X and it closes. Perfect. I launch again the mandelbrot. I press ask and it closes. That's marvelous. But let's check for leaks. So I have to do valgrind fractal mandelbrot like that. Of course, it requires more time. I'm gonna close. Okay, I don't have any leaks. Let's do again with ask, but of course it's the same thing because we have the same function that gets sparked. So ask. Okay, we managed to close the process in a clean way. So Vim events, there won't be leaks. Perfect. So now close handler is done. I have to uncomment this. This is the amount of iteration. Let's try out immediately the amount of iteration and now it changes the look. So let's launch mandelbrot. I press plus, plus, plus. As you can see, I get the colors that are changing all the times because the way we did it, right? Look how beautiful is this one. This one is sick. So the thing is that here my virtual machine is pretty slow, but we don't care about that. So performance-wise, we don't care. We just want to understand how it works. Maybe RP2 I will do also the bonus part, and we're gonna make it super fast using multi-threading and optimizations. Okay, cool. It seems it works. Now we have to zoom in. So this is my key handler, and we need our mouse handler. Okay. So for the mouse, we have this specific prototype. Okay, let's start. So we're gonna do int mouse handler. We get button, int x, int y. These are the coordinates of the mouse, and here we have the usual pointer to our fractal. Nice. So the pattern is understood, right? If button equals something, else if button equal something else, you do something else. Nothing real fancy. At the bottom we do a return 0, and there must be a fractal render to refresh, okay, with the new data. Okay, first of all let's understand the actual button presses. So I'm gonna comment this and I'm gonna simply just call printf the button that we're gonna. Of course I have to bring the prototype into the header file. It's kind of tedious, but we have to do that. We just pass here. Okay, I compile, I launch, and now let's check. I'm gonna go up and down with the mouse, but nothing really happens. What's the issue here? Did I compile? Nothing, I don't get a response. What's the issue? Let's go back to init. Sure, the problem is here. There it comes. I still have this commented. So basically my application wasn't listening to mouse events. Okay, save. Let's go back. Let's recompile. Let's launch again. Now I'll move the mouse and it goes pretty well. So if I go up, I get 5. If I go down, I get 4. So 5. I want to go deep. I want to zoom in. If I move up like that. If I go down, I want to zoom out. Okay, let's implement this stuff. So the events. So if bottom is equal to, there must be bottom 5. Here, of course, you have the symbol. I want to zoom in. Zoom in. Else if zoom out. Okay, here is bottom 4. Bottom 4. Perfect. I can delete this. Now let's understand how we can implement the zoom. So if I want to zoom in, the thing, as you already may understand, is to tweak the values coming out from my map function, you see. So I have my range, which is -2 plus 2. If I make the range, for example, -1 plus 1, effectively what I'm doing, I'm zooming in, right? Because I see the mandelbrot bigger. It's fairly easy if you watch the coordinates inside the mandelbrot set here. So decreasing the range coming out my map function is effectively increasing the zoom perception. On the contrary, if I want to zoom out, I just have to do the opposite, you see. I just have to increase the range. I just go from -2 plus 2 to -4 plus 4. That's it. So here we need the factor. So let's go to fractal.h, and inside our struct, we are gonna add another hook member variable, which is our double, of course, that we call zoom. Perfect. Let's go back. In our init function, we are gonna init this value fractal zoom equal to 1.0. One, because I want to use this as a factor. We talk about factors in multiplications, so you will understand why we are doing what I do. So this is the zoom factor. Now, where will I use this boy? Of course, in my render function here with my map. So I have the shift that is basically like a joystick, is moving the mandelbrot set inside the window. But here I want to scale my map values. I want to do that. So let's open a brace here, and let's say this value per fractal zoom closed. What is this stuff? Well, this operation here is a scaling. We have also, of course, to do this operation for the y component. Here it comes. So all my map values, which are in the range -2 plus 2, are going to be scaled depending on the zoom factor. Let's see a little program that now I make to understand this point. This is a simple program to show the difference between zoom by addition or zoom by multiplication. So basically I have the number of iterations here, which are 20, and I say the zoom is equal to 1.0. Then I say this for loop, a loop that reaches 20 iterations, and every time I add 0.1 in my zoom, okay? I do the same trick, but this time I don't add, but I multiply. You see, I multiply per 1.1, and here I multiply per 0.9. Here in the contrary, you have zoom 0 plus 0.1, and here zoom minus 0.1. So I use sum and subtraction. On the other hand, I use multiplication. Let's see the output. So here I have the zoom with the sum, and I reach, with addition, no problem, I reach the value 3, so I have the zoom per 3, okay? The problem arises when I use subtraction. You see that the value gets flipped, and this changed the sign. This is not good, because here I don't want fractal zoom to change the sign. This will mess with my sign here, and this will flip eventually my mandelbrot. Contrary, if I use a multiplication, I get this behavior. For multiplication, positive multiplication, I go up toward infinity, and for negative multiplication, I get this behavior. Basically, I never go negative, and that's the point. I go toward a very, very little number, toward infinity, but never I got flipped. I get this asymptotic behavior. Basically, I never reach the minus. I go toward a number. These operations, of course, are going to be exponential, and this is pretty cool because as long as I go deep inside my fractal, I will get the zoom factor, which is going to be tinier and tinier, tinier and tinier. So you can go very deep in your mandelbrot, and you will get that tiny decrease of your zoom factor. Okay, this maybe it's confusing, but let's try it in code with practice. Maybe it's going to be easy. Let's go to events. Now I say, if I want to zoom in, I have effectively to decrease the size of my mapped value. So I say fractal zoom per equal 0.95. Effectively, every time I decrease the range, I make it more tighter. On the contrary, I say fractal zoom gonna pass it, per equal 1.05. These are values that you can change depending on how you want your application to look. Okay, let's try this. Let's try how it works. I compile, and now we launch. Okay, I've launched mandelbrot. Now I scroll the mouse. As you can see, I can zoom in. This feels very clunky, first of all, because I have a virtual machine here. The code is not optimized. My computer is slow. I have OBS opened. So it's a mess, my friend. Hopefully in your computer, this is going to be faster. Long story short, I can zoom in. Okay, it works. Let's try zoom out. If I zoom out, as you can see, it works. Now let's try to go a little deeper here. So I zoom. Okay, we are in these tiny places. What happened? Oh, I see. I pressed the arrow, but I didn't scale the arrow shift. Boom. But I got in a totally different place because the shift is not scaled. Now I will show you why. By the way, here we can zoom in, still zoom in. I press plus to change the iterations. As you can see, I get all these marvelous shapes. The more iterations we do, the more our code requires time, because for every pixels we have every time 10 iterations more. Okay, so our fractal zoom works. The only thing is that when I apply the shift, I want these values as well to be scaled. So I do 0.5 per fractal zoom. Fractal zoom, for example, if the fractal zoom is 0.000, I don't get a shift of 0.5, but I get 0.00. You understand, right? So when I have a really deep view, I'm gonna shift proportionally as the zoom is. Okay, now everything is scaled. Let's try again to launch. Let's launch it. Now I zoom in a little bit and I check if the shift is tailored proportional to the actual zoom level. So I zoom in, here we go deep. This requires ages to zoom. Okay, we are here. Now I click the shift, right shift. So we are here. Now if I press right, you see that the shift is proportional. Even though I am on deep land, I have a shift which is proportional to the actual zoom, and this is perfect. Okay, here we are. I guess we already have basically the application. So fractal in, fractal random. Now we have to do Julia, right? We have to do Julia, and to do that, it's fairly simple because the code is exactly the mandelbrot one, with the only exception that, let's go here, Julia. I have to iterate my function in this fashion. I have z, which is the actual pixel pointer, and c is a constant. That constant is the one we are going to use at the command line. So it's going to be fractal Julia real imagery. Okay, so this constant is going to be this complex value that we take. So first problem for Julia, we have to implement a function alpha to double, right? We have to take some strings and convert them to doubles. Let's do that. So we go to math utils and we are gonna implement the function. This is exactly like a toy, alpha to integer. The code is a little tweaked because we're dealing with real numbers, but I leave you the code to my iToy. Now I write directly the code and we do a fast explanation because my brain starts to melt. So one quick thing, I think that it's better to put this function not in math utils, but rather in string utils, because you're manipulating strings. So we're gonna put here. Okay, magically we have the function. Here it comes. So it's very similar to a toy, as I told you, but we're dealing with flows. So the thing is that I made an integer part and a fractional part to be extremely pedantic. Here I have a power that we're going to use. Then the sign, the usual thing. So this is while is space, written in this fashion. So until I have spaces, you just keep going on. Then you say, check the sign. If the sign is negative, you're going to put to negative. Then you say, until the string is the integer part. So until I don't stumble upon a point. What do? Well, you just perform the simple atoy. So you're going to multiply pretend the integer part, which is initialized to 0. So this is effectively like a shift operation, right? And then you just add the actual char minus 48. You know this stuff super well, right? You point a char, for example, char 0 as the value 48 in ASCII code. So you're going to decrease by 48 and you get the actual integer value 0. Then you say you will have a point at this point. So you just skip that and you start to continuously add the fractional part to our integer. So you calculate the fractional part, which is 0 initially, and you add the value of the chart pointed per power, which is going to be every time be divided by 10, so I get 0.1, 0.01, and so forth. At the end, I just add the two parts and I multiply per the sign. Nothing really complicated. So with this function, I can take the inputs from the command line. First of all, I have to put this in string utils, so I'm going to copy. We go in fractal.h, and in string utils, we're going to put this alpha to double function. Now in my main, what I'm going to do is that I want to take the doubles coming from the input, but I need in my fractal.h to put these values, which are going to be a double, which I call Julia X, and double Julia Y, like that. Okay, now back to my main, and just beneath the name I do fractal Julia X is equal to a to double argument vector in position 2, right? We do the same for Julia Y, a to double argument vector in position 3. So we are converting the input coming from the command line into these doubles. Now let's go back to our render function. And here I can do a simple thing. The mandelbrot set initially as this, right? Z equal z squared plus c. So what do I get? That z1, so the first iteration, is equal to basically c, right? C plus c. I got this point. So I can basically skip the init part in which I put 0, 0 here. And immediately in zx, zy, I'm gonna put this value here. See, I can do like that. Zx and zy. And this I can remove. Now, for c, for c, we're gonna do a function that I call mandelbrot, mandel versus Julia. And I put as an input the address of z, the address of c, and a pointer to the struct. Okay, let's implement this boy here. Just here upstairs. I call it easy toggle mandel and Julia. Here, of course, this is going to be a static function because only here is going to leave. Void mandel versus Julia, and we take 3 pointers. Type complex, we have z, the complex c, and type fractal, the pointer to that, and we're ready to rumble. So I say if string compare, so this string compare fractal name, okay, is equal to Julia, like that, 5. Of course, here I have to invert the logic as the string compare is built. What do? You take c, so you say c x is equal to fractal Julia x. You do the same with y, Julia y. So effectively, we are gonna take the inputs. Else, what do? We have c x, which is equal very simply to zx, and cy is equal to zy. Okay, I think we are okay. What happened here? Of course, here I need the arrow. Okay, so this very silly gimmick, Mandel versus Julia, should make the trick. Should make the trick on using the same code both for mandelbrot and Julia. So of course, it's not perfectly designed because it is equal to a function. We have every time for every pixel to check this, but let's try to check first of all if it works. So I compile. So let's do fractal Julia with these values, minus 0.8, 0, 156. We get this object here. Let's search on Wikipedia if it's correct. So it should be this object here. And I think it's exactly that, right? We have this curve here, which is exactly the same. Let's increase a little bit the resolution. Okay, seems like it's working. Of course, I can move and so on. Let's try with other values. Control C. So let's do fractal 7269 1889. Okay, let's try to launch. And basically we get this object, I assume, right? It's basically it. Okay. Now, given that I'm KO, we're gonna just do one last thing. We're gonna go back to events. or better, we are gonna go in our init. We're gonna add another hook. Now you will see. Our event is gonna be this one, motion notify here, and the mask is gonna be this one, pointer motion mask. And the function that we call is gonna be Julia track. Okay, let's go to implement Julia track. Basically, this is tracking the mouse movements. Let's go to events, mouse handler. The actual prototype that we can use is this one. So we are gonna do that. Track the mouse to change Julia dynamically. So int track Julia, int x, int y, and type fractal pointer fractal. Cool. Now I say immediately if string compare, the string is exactly Julia. So what do we do if the string is exactly that? I say fractal Julia x is equal again to our map function that takes as an input x, all the same jazz of the render function, right? -2 +2 0 and width. We have to scale it for zoom plus the shift, x shift. Okay, we do the same for y and we change it to y. Here we invert, so +2 -2. Here, contrary to the mandelbrot set, it will be visible that the image is inverted. It's not correct. And here we put height. We change to y. Perfect. So we take the inputs coming from the mouse dynamically. We map them accordingly to our zoom, to our shift. And we say that our new Julia X and Julia Y are going to be these values. Then, of course, we have to render. So fractal render like that. And we have to return 0. All right. Here, maybe to make the code more readable, I just do like that inside here, even though it's the same. All right, let's try to compile after putting this in my headers. So new fractal headers, past it. All right, let's compile and launch. What is the problem? Julia track. Oh, I undeclared. I wrote here track Julia. Oh my god. Julia track. Okay, back to our page. We do the same, Julia track. All right, now we should be okay. Okay, let's launch again our Julia. And this time, as I move the mouse just above the image, it should change dynamically. Okay, of course, this is gonna take ages to do its stuff because my OBS is killing all my CPU processing power. This is a virtual machine and I just want to understand if it works or not. As you can see, as I move, the Julia set is changing accordingly. Hopefully in your system is gonna be faster. Let's try again. Okay, it's moving, it's super slow. So I just made the really fast analog code. I just copied the Linux one. I just made some changes. And now we're gonna check in macOS this behavior. As you can see, this is what we are gonna get. As you can see, it moves dynamically depending on the position of the mouse. You see? All right, my friend, that's it for this very long. For you, hopefully it's gonna be shorter. I'm gonna cut all the silences, but yeah, that's it. It works. It's not optimized. It's not perfect. This is something that just works. I hope you got some principles, some ideas for you to solve this program. And please, in the comments, just tell me, hey, you can do this better. You can do this other point much better. We are in this stuff all together. I'm gonna push this stuff on GitHub so you can watch the code. I'm gonna add something maybe this evening because now I'm kind of destroyed mentally. As you know, coding for a long time breaks your nervous system. So you can check the code, but the overall ideas are all in the video. So, my friend, thank you for watching. Enjoy.